Welcome to qnawire.
This is problem number 24 of chapter 23. In this problem we have two glass panes separated by air here, and we're going to label that separation between the glass with T equal to 150 nanometers. The question asks the wavelength of what light yields constructive interference and the wavelength of what light will destructively interfere. So here we have N glass, N air, N glass. The refractive index of glass, we're going to go ahead and take that to be greater than the refractive index of air. So as light comes here from the glass, the majority here gets transmitted, but then there's a portion that gets reflected. Since we're going from a higher refractive index to a lower one, there is no phase shift associated with this reflection. However, for the transmitted portion of the light here, now it's in air, it's going through air, it strikes the glass. Since it's going from lower to higher, this reflected portion does experience a phase shift of 180 degrees. So a phase shift of 180 degrees, we can write that as a path length difference of delta reflection, which is equal to lambda over 2. A phase shift of 180 degrees is the same thing as shifting the wave by lambda over 2. So the wave continues here. This 180 degree reflected ray keeps on going through the glass, and then it comes out the other end. Now, since it comes and it's transmitted through this glass, we aren't worried about a phase shift because it's transmitted. If we were worried about a reflection here, then it would also be shifted by 180 degrees again, but we don't care about this tertiary reflection. We care about the combination of this first reflected light and this other ray here. So the net path length difference, let's go ahead and call that delta. It's going to be equal to the path length difference associated with the reflection plus the path length difference associated with the light going through that column of air. Let's call that delta T. Now, for constructive interference, the net path length difference must be equal to an integer multiple of wavelength. So if the path length difference between these two rays is 0, they constructively interfere. If it's lambda, they constructively interfere, and so on. So here m is equal to 0, 1, 2, 3, 4, etc. However, let's go ahead and expand this term. Let's go ahead and replace it by this. Lambda over 2 plus delta t is going to be equal to m lambda. Okay, so this is telling us that half a wavelength plus this is going to be equal to an integer multiple of wavelengths. The only way that can be true is if delta t is equal to an odd integer multiple of half wavelengths, because halves plus halves gives you whole numbers here. So let's go ahead and write that out. We get delta t must be equal to an odd integer multiple of half wavelengths. So in this case, m is going to be equal to 1, 3, 5, 7, etc. Odd integer multiples, because odd integers here plus half a lambda it's going to give us integer lambdas here. Delta t is going to be equal to 2t because that's the path length difference. The light comes in and then it comes out. So here notice that since this column of error is very narrow, we're assuming that this distance here is equal to this one, which is equal to t. So this is true as these glass plates come closer and closer together, and light is going to be coming in at an angle. So this is drawn in an exaggerated way. So we're assuming that this leg is equal to this leg, and they're both equal to t. Okay, so 2t is going to be equal to m lambda over 2. If we solve this expression for lambda, we get lambda is going to be equal to 4t over m, where m is restricted to these odd integers here. If we go ahead and set lambda equal to 4 times the thickness, which is 150 nanometers, and we divide it by the lowest number m could be, 1, in this case for delta t, not to be confused with this m here, but this m here, we get 4 times 150, which is 600 nanometers. So wavelengths of 600, light of wavelength 600 nanometers is going to cause constructive interference here. So that answers the first part of the question. This is for constructive interference. The second part of the question asks, what is the wavelength that will destructively interfere? Before we move on, let's just make a note that if we go ahead and change m for any of these odd integers, we would also get a wavelength that would constructively interfere. Okay, so now let's move on to destructive interference. Let's change color here, I guess, to green for destructive interference. The net path change, the path length difference must be the same expression here, this first part. However, that sum must be equal to odd integer multiples of half wavelengths. This is for destructive interference now. So m in this case is going to be equal to 1, 3, 5, 7 odd integers. What's going on with the light here with the reflection? That stays exactly the same. Light comes in, it reflects, no phase shift. The part that gets transmitted hits this, gets 180-degree phase shift, and then it gets transmitted through here. So the net phase shift is going to be, the net path length difference is going to be the lambda over 2 associated with that reflection, with a 180-degree phase shift at this point, and delta t due to the light traveling through the air. Twice t. Okay, so let's go ahead and repeat the process that we did here. Let's move this down. Lambda over 2 plus delta t is going to be equal to m lambda over 2, where m is an odd integer. But lambda over 2 is odd. It's an odd integer multiple of lambda over 2, 1, right? So if we subtract this from this, the only way that this can be true is if delta t is equal to m lambda, where m is equal to 0, 1, 2, 3. So just the regular integers here, 0, 1, 2, 3, etc. So this m is not to be confused with this one. Okay, so if delta t is some integer multiple of lambda added with lambda over 2, we're going to get an odd integer multiple of half wavelengths here. So that's why we're changing m here with respect to this delta t. So again, delta t is equal to 2t, and this is going to be equal to m lambda. So we're going to get destructive interference here. Let's see. Let's go ahead and solve for lambda. Lambda says 2t over m. So here we see that m cannot be equal to 0 because otherwise we would get lambda approaching infinity. So let's go ahead and erase that. So if we set m equal to 1, we could go ahead and solve for the lambda. We can go ahead and solve for a wavelength that will destructively interfere in that air column. So let's go ahead and set m equal to 1. So if m is equal to 1, let's go ahead and put all the values here. So it's going to be 2 times the thickness, which is 150 nanometers, divided by 1. It's going to be equal to 300 nanometers. So wavelengths of 300 nanometers are going to be destructively interfering with one another once they reflect off the glass here, and once they reflect off the glass here, then when they eventually combine here, they're going to do so destructively. This concludes problem number 24.